To open results in Geodict, we have two options. The first of all is to go under File and click on Open Results and then navigate to Results. Or you may also choose the Open Results in the menu bar by clicking on it. Then we navigate to the workshop folder, which has been provided, and we click in the flow simulation folder. And here we double click on the complete filter flow underscore workshop.gdr, which is the result file folder for the simulation. We see directly in the report the applied volume flow rate with 0.83 liter per second. We see the average flow velocity over the inlet, which is 2.8 meters per second, as well as, most importantly, the pressure at the inlet, which is around 21,000 pascals. From the numerical side, we see how many threads we have run the simulation on, how many iterations have been used, as well as the runtime of 1.4 hours. Last but not least, we also see the memory usage of 38 gigabytes, and we see that the solver stopped successfully for error bound, which gives us the feedback that we don't have any errors in our calculation. To visualize the structure in the flow field, we click on Load Structure. This then loads the initial structure, which is the same as presented here, but then we see here a green light, which shows us that we have the exact same structure. We then go under Flow Visualization and click on Load, which loads the velocity and pressures. We then can specify the data which we want to load. In our case, we are only interested in the velocity. Pressure can be also simulated. And then, so we deselect the pressure and then we select OK. The loading of the velocity field takes around 3 minutes. After the volume field has been loaded. It asks us if we want to set the material ID 2, 4, and 5 to invisible. We decline this by clicking on No. And then we click again on the field, and we see that we have now next to the structure field also an additional volume field. We now want to see how the velocity field is situated in the 3 dimensions. So we can, for example, clip here in the y direction the structure, say to some value which is like close into behind. So we see, for example, the slice 335. We then move on to the volume field and select the same slice 335. And we beautifully see next to the structure that for the inlets we have very high velocities which go past a smaller channel here, which increasingly shows high velocities, and then the material moves through the pleated filter media and then discharges for the outlet in the middle. So from the 3-dimensional perspective, we are quite confident about results. By moving with the mouse over each voxel, you see the velocity in each of the cells in meter per second. The same can be done when we have the 2-dimensional view. So for this, we crop back the velocity field to the first slice 0. The same we do for the structure by changing to the structure tab, set it to slice 0. We then go for the 2-dimensional representation. We switch off the structure. And then can move through the structure by scrolling with the mouse pad. And see exactly that, for example, the structure rotates through the netting inside and how the velocities change throughout. This is, for example, one very good control mechanism to see if each of the pleats has flow inside, so we don't have any pleats which are stuck together. Do the voxelization method and then are clogged. This sometimes is quite tedious when, for example, we have very low resolutions and then voxelization is too coarse. So in the end, pleats can be stuck together and no flow can enter, but in our case we see that each of the pleats has flow inside. The next step, after the flow simulation, which can be done within a few clicks as I showed to you, we now will generate a pleat structure, which we then substitute into this original structure and then run another flow simulation to see the difference within the pleated structure. So to prepare the next step, we go under File and we discard the triangulation to free some space in the memory. And the same, we discard the volume fields and we check back the structure by clicking again the structure. To now generate a pleat structure, we go under Model and we select the Pleat View module. And then we have two options. The first option is the already known version where we have rectangular pleats. So for example, in cartridges, which you could specify here. But the new feature in Geodude 2023 is the generation of cylindrical pleats. So we select the cylindrical pleats, and to specify the options, we click on Edit. Here, as always, we specify first the results file name and give it some meaning which we can recall afterwards. In our case, as we already had like a pleat structure with 56 pleats, we want to have here a pleat structure with, for example, 54 pleats. So we give it the attachment for the results file name. And when we then look at the options, we see on the right hand side very presently a sketch of the pleat which we are going to generate. And if we change one of the parameters here, the sketch automatically changes and shows the feedback we generated with the changes. In our case, we select here the pleat pack inner radius as 43.35 millimeters. We specify the pleat pack outer diameter, so the diameter here on the tips to be 67.75 millimeters. The inner radius at the pleat valley specified here, we will change to 0.4 millimeters, and the inner radius at the pleat tip is here on top, which is set at 0.5, so we leave it here. The pleat count we set to 54, and the pleat pack height we set to 85.02 millimeters. Especially to this pleat geo options is also that we can not only generate cylindrical pleats by itself, but we also can check the M-pleat pattern, which is quite well known in the industry. So when we, for example, click here on the M-pleat pattern, for example, Geodude directly generates an M-pleat pattern, which means that not each of the pleat is at the same height. We, for example, can then optionally, additionally to the other options, specify a short to long pleat number ratio. So for example, if we have now a ratio of 1 to 2, we have always 2 large pleats with 1 shorter pleat. But for example, we can also increase this to 1 to 3 ratios, or to just 1 by 1, which then has alternative 1 large and 1 small pleat. Here also we can have the ratio of the height of the pleat. So if this, for example, is a fraction of the total size of 1 long pleat, and the pleat count is the pleat count which has one of the eternals. So if you have 1 to 1, we have 16 pairs of pleats. In our case, as we have in the oil filter classical pleat without the M-pleat pattern, we deselect this option. I just wanted to show and highlight the functionalities which can be additionally chosen in the pleat geo module to you. And then we move on to the next tab, which is the general tab. Here we can specify different layers of porous material if we have, which accumulates. So in our case, we will have only 1 medium layer, and this will have the thickness of 0.6 millimeters. For example, optionally, we could also specify here already the different materials if needed. Then we move on to the domain tab. Here we first of all specify which fluid we are going to simulate. So in our case, again, this will be oil. And we can specify the voxel length. So the voxel length ideally should be the same as we have in the complete filter, so that both numerical resolutions are the same. So we enter here the 109 micrometers we have in the original CAD structure, and Geodict automatically calculates then the total domain sizes. The input parameter already shown, of course, are dependent on the original structure. So once the original structure needs to be imported, then some of the parameters, of course, need to be known in this kind of sense. Last but not least, we click to the Output tab. So here we can specify specifically the quality of the mesh or the structure which is generated. So for example, we can, by default, we have 6 segment numbers per half arc or per line. So this means the density of points. In our case, the 6 is totally fine as default. But in cases you have very narrow pleats or very thin pleats, this might, for example, be an option to change. The same we have automatically an export as STL. So this we will always leave on. And also we can specify the unit in the file. So for example, if you might recall, in the original CAD data, we had the unit of meters in the CAD data. Here we'll leave it as with millimeters. So to show you then when we import the structure, the pleat structure in UNIT, there's no problem also to select a different length unit in Geodict. And if you have finished, we click OK. And then normally we would click Generate. The generation of pleat structures here lasts around a couple of minutes. But to save some time, I already pre-generated the structure. So we don't hit Generate here, but we'll open the data from the provided data set. So now in the next step, we want the generated pleated structure to be inserted in the original structure. And this should be a one-to-one replacement. So we want to reassign in the first step the existing pleat structure and then insert the new structure with either different pleat count, which is in our case holes, but we could also have different thickness or a different amount of porous layers which you could insert here and then have a new structure here. Geodict offers in this case 2 possibilities. So the first one is when you use PleatGeo, you always get like a resulting GDT, so a structure file. So this can be imported, but to stay consistent with the also existing structure, we'll use the STL, which is exported from the PleatGeo, to show you that we can also use different STLs and set these within each other. So to do so, in the first step, we're going to reassign the material ID 2 to material ID 00 oil. As we have done this already, so we go under Model in the menu bar and we select again Process Geo. As a sub-function, then we choose Reassign and reassign material ID. We open the options by clicking on Edit. And we select as the old material, material ID 2. And the new material ID, which should be reassigned to, will be the material ID 00 oil. And then we hit OK. And we click Reassign. Now we see already here in the 2D view that the pleated structure is not existent anymore because we converted it to the material ID 00. We could also switch to the 3-dimensional view and crop a little bit into the structure by clicking the Structure tab here and then crop a bit from the right hand side, and we see that the oil filter is empty in this case of sense. So now in the next step, we want to use the pleated structure we generated in Geodict to be inserted at the exact location here. For this, of course, already the knowledge of the original CAD is necessary, as we need to know the shift of the pleats which we'll be entering in the import GeoCut. To insert the STL data we generated in PleatGeo, we again click on Import in the menu bar. We select Import GeoCut, as we did for the generation of the original, or like the import of the original CAD data, and we click on Browse. Here we navigate again to the provided folder. We click into the generated pleat folder. We double click the cylindrical pleat workshop, and we'll find a cylindrical pleat underscore 1.stl, and we double click it. Now in the beginning we want to import only a surface, because STL files are a surface file, and then we have the optional mode for the surface. So here we don't want to create a new structure, we want to keep the existing structure and have a mesh. So now we see that the lengths in X, Y, and Z are kept constant, so we cannot change them anymore. In the following now, we specify the unit in the file, which we have set in the PleatGeo when we export it in STL. So this is millimeters, which is correct here. And then we enter the shift in X, Y, and Z. And these data need to come from the original CAD, where we already have one pleat inside. So these values should mostly be known in each case. In our case, we will set here as the shift in X 37.823 millimeters. We set the shift in Y to 37.714, and the shift in Z will be 52.107 millimeters. We then want to have the material ID not to be the same as the solid parts. So we want to specify it as a different material ID, as we again need to have it as a porous material, which we will let the oil through. And for this reason, we set it here to material ID 2. And then we click on import. We will get an immediate warning that the structure wants to be set to visible. It might intersect the surface mesh, and it asks us if we should set the structure to invisible, and we decline this by saying no. Because we want to see both. We want to see the pleated structure here as a surface triangulation, which is represented by the triangles tab here. So we can switch it on and we can switch it off. And all the remaining parts which are already voxelized as a structure, which we can also switch on and we can switch it off. Now we can have a first look if the structure is already fine from a qualitative standpoint, but the next step would be to have this structure here instead of triangulars. We want to have it in a voxelized base. So then also the material will appear here in the ID section. So for this, we again go for model, and we select the Mesh Geo module. This is for creating meshes out of triangulations or triangulations itself. Then we click here to select the functions, and we select the functions voxelize mesh. To open the options, we click on Edit, and Geodict already automatically assigns material ID as we have chosen. We want definitely to keep the current structure here. You could specify, for example, different voxelization methods, all at once or per object or per component. But in our case, as we have only one mesh, it's totally fine to have voxelize at once open. You could specify here, again, different methods or like material IDs. But in our case, as we just had the material ID 2 set to be oil and manual, it would be beneficial or very easy to leave it as this, and Geodict will correctly assign it automatically. And then we hit OK, and then we click on voxelize. This should take a couple of seconds, not too long. And then we can make a quantitative check if the pleated structure is inserted correctly at each location. So after the voxelization is finished, we can have a closer look, because now we can switch off the triangles. And when we now go here under structure, we might again crop here in the Z direction. And we now see also that the pleat can be cropped. And now we can have a more in-depth view. For example, if you now go back and deselect the clipping in Z and want to have a clipping, for example, in Y direction. So we clip here the Y direction. And we could, by scrolling with the mouse, we can see, for example, that the pleats perfectly fit inside of the netting. So this is the precondition. So you need to have the original data valid, so that the original data gives more or less, for example, for complex complete filter medias, the data and the shift in X, Y, and Z direction, because this is something we need to know from the original CAD data. The same holds for the pleat structure itself. So it's mostly the pleated structure, or like the height of the tip, is somehow defined by the housing parts, which might be also flexible in your case, but mostly have defined height or size. So in general, this approach is here to check the inference without producing any pleated structures. For example, how would the pleat count influence the pressure drop, or how would additional porous layer influence or affect the pressure drop of filtration relevant parameters. Last but not least, we can save the structure again. So we can, for example, click File, click on Save Structure As, and we can select a name with pleat structure underscore 54 pleats, for example, or something you could recall. And then we save the structure. And now we have two structures, one with 56 pleats, the original CAD, and now one with 54 pleats. So again, you could click on Predict and set up a flow simulation and individually test it in Geodict to get a specific case. But when running, for example, parametric studies, you may want to create in the similar fashion several geometries, maybe for example ranging from 50 to 60 pleat counts. You want to have like maybe the thickness changed of the pleat, individual pleats. Maybe you want to also try one of the M patterns to see if in your case, for example, an M pattern pleat would have some of the parameters which you want to achieve in your performance. And then when you have all these geometries generated, you could run it either by Python systematic simulations. So Geodik would run each simulation after another, or when taking, for example, the cloud computation capabilities all at once. Also, the structure generation can be automatic scripted by Python. So this generation of the pleat, the variation of the parameters can be set as an array of changed parameters, and everything would be done in Geodict. Of course, the input parameters would need to be given once. The import filter SCAD needs to be checked once that everything is correct. But for this purpose, for example, you could also use one of the safe structures which already have all the inlets, outlets specified. In this workshop, we generated a cylindrical pleat structure with different pleat count and substituted it into the original structure. Using this feature, we are able to generate various geometries beforehand without using additional third-party softwares. To further increase the productivity in large parametric studies, the structure generation can also be automated using our Python API. Here we can set an array of parameters which we want to vary, and the structures are generated automatically. To even further increase the productivity and shorten simulation times for very large parameter studies, the cloud capabilities in Geodik 2023 can be used. This has the advantage that some simulations are all performed at the same time, which results in one runtime for all simulations instead of sequential execution one after another. Thank you for your attention during this workshop. If you have any questions, please feel free to use the chat or contact us after the user meeting. We now have enough time to answer some of the questions and discuss. Thank you.